Okay, good evening everybody. My name is Claudio, I'm a software engineer at Banksealer. So I will talk to you about the software architecture of Banksealer and the algorithms behind Banksealer. So essentially Banksealer is a system that moves a transaction to different states. So actually the main entity in Banksealer is a transaction. The transaction is like a bank transfer or a payment, or we also consider a login to a platform a transaction. I mean, whatever is a record for us is something we can process and we can analyze. So here you have, in the middle, the main path a transaction goes through in Banksealer. So we receive an input transaction that can be anything the bank sends us. So in this state, we are taking this thing from the bank. So this is in raw format, so we need to do something with it. We need to process it and validate the content so that we are sure we can do something good with it. We're sure the values are correct and properly formatted. So once we're done with this job, we have process transaction. This is probably the most important format of our transaction. We use it for giving it to machine learning algorithms. We use it for the training phase and so on. At one point, we score the transaction, so we attach a label to the transaction. That is the, let's say, the score, the score of the anomaly, how anomaly is the transaction. And then after we're done, we write back the transaction to an external system, to the system of the bank. So actually here we have different ways the transaction, the score we produce are visualized. So we visualize the transactions in our own system, as you saw earlier, but we also send the transaction to third-party systems so that the bank can use the transaction as it's used to. So we also send this transaction to Elasticsearch, so that the fraud analyst can go through the transaction, the historical, and do some analysis on what's going on. And another part is the static rules, as Daniele said before.
This means that you have a database of existing transactions?
That's right. Actually, we are keeping a database for different reasons. So we have a relational database, I have it here, for storing historical transactions, so that we can use them for training our models. But we also insert the transaction to Elasticsearch, so that we have a proper means for searching information. So to accompany the transaction through its life, we need several processes. The first one is an import process that is used to take the transaction from the bank and introducing it into our system. This particular service is ad hoc per bank, so there is an integration job for that. So we can receive the transaction in very different ways. For instance, we can take it from a database, or we could take it from some file, or maybe we are receiving push that transaction. Another fundamental part is the scoring. So as soon as we receive the transaction, we try to produce a score, because the system is also running in real time. So we need to produce a score as soon as possible. And this is done by this model. The score is produced thanks to machine learning algorithms. So we have a process for building our models and updating them. This is what we call the core, so the main part of Banksealer. But we have also other components. For instance, we have a user interface and we have a backend for that user interface. We also have several maintenance jobs that are used to maintain this database, because we have several transactions and data and we need to clean sometimes what's going on, or rebuild indexes and so on. And the same holds for Elasticsearch. Any question about this, about how the services work and so on? Okay. So in Buildo we use Scala a lot. We also organize a Scala meetup. So all the services are written in Scala. The main reason why we use Scala is type safety. It's a nice property. It means that when you compile your code, you get type errors. So if you're passing a string to a function that takes an integer, you cannot do that. You immediately notice it. So you're pretty sure that what you're writing is correct for this kind of errors. So it's pretty useful for refactoring for a wide range of use cases, I'd say. We have, as you've seen, we have different services. This is pretty useful for different reasons. For instance, for deployment, when we want to deploy a new service, we don't need to stop and do something with the other services. The other services go on running and they go on doing their job, but we can anyhow deploy new things. Actually, we are a startup, so we are still developing several components that are useful, and that's pretty important. Something pretty important in our project. We are using Docker. Docker is very important for also for the deployment, because it makes very easy to solve system problems. For instance, you don't need to fight with the architecture of the machine or with other dependencies. What we require to our customers is just to have Red Hat installed or something that supports Docker, and then we do everything. So an interesting part, and that's the reason why I liked the components we've read, that is the components that communicate with external systems, are what we call the drivers. So we mainly have two components: the core, that is what is generic per bank, not specific per bank, so what is the same for any use case and any installation we have, and the drivers that are the specific implementations. So we have a few modules, such as the score transaction or the import module, that have a small component attached that is a dependency, I'd say, that is something that is written ad hoc for the bank, what I seen earlier. So we actually write the code for going and taking the transaction for the external system, or to write the transaction to an external system. So this is something we learned working on Banksealer. At first, we implemented when we started Banksealer, we decided to use the database as a queue. So when you take the transaction and you're writing a data pipeline, I'd say, you need to store the transaction somewhere. And you need to flag the transaction that you already processed and what you've done with those transactions. Actually, you need a queue, okay? And what we did was to use the database we had as a queue. And we found out that this is not working really well, okay? So what's the reason? First, you need to implement a queue using a database. So you need to add a flag on the database, a field that a process field that you use to keep track of what transaction you already processed. Second thing, you need to clean the queue. So you have a process that runs on the database and performs some queries. And this is not hard, but this is not something you want to do. I mean, there are queues. So Kafka or RabbitMQ, and it's better to use the proper tool for the proper job. And we are currently, we started 2 months ago working with Kafka, and we are trying to move from this model to Kafka. So this is just an interesting architectural pattern we discovered that way. Another interesting thing we are doing is Wire is a library we wrote that we are using in build a lot. So as I said, we have a data pipeline, and it's very important for us to have queues, but sometimes you need to pull the data and not to receive the data in push. In these cases, we use an RPC style approach. So this is useful for both web to server communications and service to service communication. What we're doing here is using Scala as an IDL. So Scala is our intermediate language. We have an interface, and from this interface, we generate the code for both the client and the server. So this is pretty easy for us, because once we have having this tool, we can just write our interfaces, and all the code for the communication part is automatically generated. We wrote actually a blog post about this, so if you want to have a look later, we can send you the link. Here we have an example. How many of you know about Scala or ever used Scala? Okay, so maybe you better understand this. So a trait is like an interface in Java. So we just have this representation. We flag with annotations 2 methods, and we automatically derive the routes, a query routes, so a get, and command route, so a post, and we automatically generate this thing, starting from this. For doing this in the backend side, everything is at compile time. So we use a set of macros and we generate this thing at compile time. For the front-end part, we use TypeScript, and we have a system that is called Metafeus that allows us to generate the proper conversion. So algorithms. Actually, this, as Daniele mentioned, we did a lot of work about this part. So the Politecnico di Milano is doing research work on this, and we are actually implementing in Banksealer a subset of the algorithms we think are better suited what we're going to do. So what are the requirements of our algorithms? So we are building a system for helping a human analyst catching frauds. So the first thing is that this tool should be useful to a human. So it's not something that's completely automatic. Second thing, it should be white box. So the human should understand what's going on. It shouldn't be a black box or something not understandable. It should be easy to explain what the system is doing. The third component is false positive. This is actually the main requirement banks have, because traditionally the problem that this kind of system had is that they report too many transactions. And if you report too many transactions, the human analysts cannot read all the transactions, they cannot go explore what's going on. Fourth requirement is it should be easy to deploy, because if you're a startup in particular and you need to find new customers, you need to be very fast showing the bank or your customer that you're good doing your job. You can't ask them for very strict hardware requirements, or they're not going to, I mean, you're not going to be able to show them what to do. So how we try to address those requirements? The first thing is that Banksealer is based on very simple concepts. We are using the main part of our algorithm is based on HBOS, that is mainly based on histograms. So we can take those histograms and show them to the analyst, and the analyst perfectly understands what's going on. So this is what we call white box approach, explainable machine learning. So this is something that an analyst can watch and understand. So we, as you saw earlier, we provide a motivation for why we reported the transaction. The second thing is ranking. This is pretty important because another problem, I mean, the main problem banks have with current system is that it's false positives. So when you have a system that shows you too many transactions and you don't know how to filter those transactions, our transactions are ranked. So if you are not sure how to check them and you're not able to check all of them, you know that the first transaction is the most risky one. So you just go from the top to bottom and you find everything you need. So it's easier to control the number of transactions you need to watch in a day, let's say. Why not deep learning? Well, this is pretty straightforward, I think, from the requirements. You need to easily understand what's going on. So you cannot have a very complex system where you have different neurons. But I mean, this is not a model you can give to someone. These teams, the analyst is also often the guy who calls the customer, the bank customer. So you cannot say a customer, okay, the neural network told me that this transaction is fraudulent. It's not something you can do. So you need good reasons and something easy to explain to the user. Another problem is training time, and hardware requirements. So we need something that is pretty easy to deploy and is pretty performant. So here we have our approach. So the approach is based on 3 main algorithms that try to address different concerns. So the first one, the most important one, is the local profile. The local profile is an algorithm that works on single users. So we analyze the data, we analyze a single user, we profile it, we build histograms that represent the behavior of the user with respect to features. So, for instance, you have a user who usually perform bank transfers of 10 euros, and you will have an histogram that shows that this user performs so many transactions of that kind. And this is what we use, as main component of our system. And the anomaly detection algorithm works like this. If the frequency is very low, so the anomaly will be very high. If the frequency is high, the anomaly will be low. The second component is the global profile. This helps when you have undertrained users. So when you have users that are new, you can't build those kind of histograms if you have a new user. So you try to see how the new user will behave. You try to predict it. How you do that? You compare this user to other users. You try to see if it belongs to a specific cluster, and then you use this information to assign an anomaly. Third, the temporal profile. This is trying to deal with a more tricky kind of fraud, that are fraud that seem perfectly normal from a behavior perspective, so a normal amount, maybe a normal perform at a normal time, and a usual day for the user, but are maybe performed more than once. So maybe you have 10 transactions, but if you take the single transaction, it seems fair and fine, but it is not. So this algorithm tries to analyze the user in a specific time window and understand the behavior of the user in that time window. So you're not taking into account a single transaction, but a bunch of transactions, and you're analyzing them together. So going more in depth in the algorithms, what the local profile works like this. So we have a training phase where we build our models, our histograms, and then we have a non-line phase that is a real-time phase where we use those histograms to produce a score. So the algorithm is based on HBOS, and what we're doing is what I tried to explain earlier. So here you have an example of the histograms. If the frequency is low, you have a high anomaly, and if the frequency is high, you have a low anomaly. What you're doing, you're taking different features, so different histograms. You're doing the same thing several times, and you are weighting together this information. This is how you obtain the score for a single user with the local profile. So after that, you understand that if a transaction have a very high amount, it would be more dangerous than a transaction with a very low amount, because you're going to lose less money. So this whole thing is biased with respect to the amount. Any question about this? Yeah.
Which features do you use here?
Sorry?
Which typical features do you use here in system anomaly detection?
So typical features are the IBAN, and we actually parse it to extract some information such as the financial institution and the user account and so on. We use the amount if we have it. If we have an access, we don't have the amount at all. We use the user agent to extract information about the device, the IP, so that we know from where the transaction was performed, and we have other information. And we often also use ad hoc information from the bank, so the type of the account and other things.
You said before that banks don't share data.
Right.
Okay, but you wrote in the middle, say that you are doing deep learning by actually feeding with the data the same machine learning, so that you can in one way reutilize it. That's the idea, correct?
Okay, now what I meant with banks don't share data is that you can't export data from the bank. I mean, it's not something you usually want to do, because you need to take the responsibility for the data.
Yeah.
So that's the reason why it's not.
You can just read them.
We can read them. The Banksealer is installed on premise, so we are actually installing the tool in the bank.
Okay.
So once we are inside the bank, we do whatever, I'd say whatever we want. So we have our algorithm, we train our thing in batch, and then we have the runtime scoring. This
so you can actually capitalize on the data set from different banks in the same training.
This is not something we're doing, because we install on premise for the specific bank.
This is something really tricky because you need to convince someone in the bank that you're doing something with their data that is going outside the bank, and usually banks are not really happy with it.
But you are keeping the memory, you know, on premise. You're not doing this on Amazon.
Me and you understand this. A bank manager really.
No, I know. You know, a bank manager by definition will never do this.
Yeah.
You know, but it makes sense. You know, this is something that should be brought at the ABI level because at the end the patterns are similar. You know,
it will be actually very helpful because the fraud pattern, this is especially true for static rules, but this is something that is already happening. The same should happen also for machine learning algorithms, especially for this second point. The number of fraud is very low. Something I forgot to say before, but one of the main classification issues about this problem is that you have tons of transactions, but few of those transactions are actually fraudulent. So it's quite hard to convince an algorithm to properly classify them. The other problem is that banks don't share fraud data, so you don't have a data set to work with. So it's pretty hard to do your analysis, to train it, and also to doing the research work is not easy. I mean, we was very lucky because we started working on this with a bank, and we managed to get their data for doing our analysis.
Because in Italy, the number of false transactions are pretty low, far lower than the other part of the European market.
It is, and actually we are mainly working on home banking systems and not on payments. Though this approach works also on payments, but we are mainly working on bank transfers. So the home banking is pretty much secure in most of the cases, but there are still situations where you want to go and catch the fraud.
How much of the frauds as a bank agent, more or less?
I think it's like 0.1%.
0.1, even more, less than that.
No, sorry, 0.0001.
It's a big.
No, okay, sorry. I was comparing to 100, so it's like 0.0001%.
Yeah, okay.
Sorry.
Change bank if you have these numbers.
Yeah, true.
Go to the next slide.
This one?
Yeah. So you see, this is machine learning algorithm, but it looks like you found a close expression for computing the score. So where is the learning bit in this diagram?
Okay, the learning part. This is actually this is kind of called a semi-supervised algorithm. So it's not. This is called like this because you have a training phase, but you don't have labels. So it's like an unsupervised algorithm, but as a process, it looks like a supervised algorithm. So the first part is the training part. You go and build these histograms. So this is anything that Banksealer is doing for the training part for the local profile. Then for the...
When you say building histograms, it means distributions of features.
Right. So for each user, for each feature, you go and analyze, count the number of times the user performs an operation.
Okay, but this is not machine learning.
Well, this is actually machine learning. Machine learning is like statistics and computation, right? This is not like this is not I'd say classification algorithm like a neural network.
Okay, I understand. So you're training because you want to learn the distribution of data you assume to be normal.
Yeah, right.
Normal in the sense that it's not anomalous.
Right.
And then you apply that distribution for a new point to see if it if it fits within that distribution. If it's outside the distribution, means it's anomalous.
Yeah, that's correct. That's pretty much correct. So we expect the user to behave. For instance, if you consider the amount is maybe the most easy example. I go back some slides and go here.
You don't only have to build the frequency. You also need to build the bounds. So this is not super trivial as it seems.
So this is more example closer to what you were saying. So here we have an histogram from an amount. This is what we're going to build. So a new transaction arrives and we're going to increase this by 1. So this is the model. When we score, we take this histogram. A new transaction arrives, we try to match the bucket. and we use the information to produce a score.
But how do you decide which feature is more important? You can take them out, you can take them out over a day, you can take some of transaction over 100 days, and you can end with an endless list of features. So if you don't have a labels, how do you do it?
Sorry, excuse me, I didn't
How
understand.
do you decide which features is more important? You try to detect anomaly, right?
Okay,
Be able to find feature which can find anomaly for each specific transaction.
Okay, this is a very good question actually, and we have. So at first we manually decide the weight of the features. So we introduce a bias on the weight of the features when we set up the algorithm, and we decide the features actually, considering the situation we are in. After that, we have like I don't have slides for this, and but we also have a feedback loop mechanism that, considering what the analyst is reporting, goes and tweaks the weight so that the score actually is closer to what the analysts want to have. Is it clear?
It's very related. So basically, I see a sum over there.
Yeah.
The more there are sum is like more regression, right? So you try to learn a weight for every feature, and with this updating, you try to optimize the weights. Always literally a sum. So every feature weights the same, and you sum them.
Well, actually, it's actually a sum, so it works like this. Is this one? But the weight is modified on the fly as new transaction arrives and as the analyst use the interface.
And have you tried to also to make a little bit more feature engineering, like okay, I have features, trying some interactions among features, trying to import, because in the end, I understand you really need to stay in a separate model, but you can try to push it a little bit in a way that also the analyst can somehow understand. So you tried also to play a little bit with the features, and so thank you. And the second question is very related to the idea of, so you said you cannot merge data from one bank and another bank, but does this guy accept that I don't share the single transaction, but I share like the learn parameters among banks, or they are also very skeptical about it? Anything you learn and you made from our data cannot go outside.
I can answer with this. You can even put USB keys in it.
Okay.
Okay. No USB keys.
You
No
need to write down the weight.
The deploy process is a mess.
Okay.
And taking out like even a bit is too complex for that.
Okay.
Even if you, I mean, if you learn a model, then you only share the parameters of the learned model. That is also not acceptable.
If you can do that, I mean, we can hire you and you can go there and ask them. We will really let them know. It's like really procedure-wise.
È il motivo per cui poi l'approccio è mostrare ranking di transazioni. I requisiti sono un po' complessi.
Sorry, one question.
Yep.
I didn't get what period you have used for doing the analysis on the transactions. For example, you're considering the transaction for 1 day or 2 days or every month. How does it work?
Okay, typically it's monthly. So we take this transaction for a month because it's a good period for. The behavior of the user is monthly. I mean, you have good frequency of operations. So you have all the operations for a user in a month. For instance, you perform some payments, recurring payments, and so on.
Or do you make any difference with the different profile of the users? For example, one user is an active user, so he's using the bank account every day. The other one is using the saving account, maybe not. Everyone is going to have a pattern as a behavioral pattern, not monthly, but maybe in 6 months or 1 year, we can see the normal behavior of him. So I'm saying that different pattern between the different profile of the users can be different.
Yeah, I understand this is pretty interesting, especially comparing private users and companies, I guess. But we're not doing that, but we are, something else we are doing that is related is analyzing whether the user is active or not, or if it's a new user. And for this we use the following component of the algorithm. That is the global profile. This works like this. We try to create a cluster of the users, and we change the sensitivity of the algorithm to progressively, incrementally create larger clusters, and we compute the anomaly comparing the distance between the cluster of the given user when we analyze the transaction with respect to the original cluster. So this is something we try to do when a new user arrives. We try to match this user to one of those groups. No, we just use some features. Yeah, it's not random. We compare it with the basic information we have about the user.
Okay. No, I'm saying it is just a new user is just using the bank account for 2 weeks. So how do you assign it to a cluster? Is it randomly or?
We have some basic information about the user, and that's what we use.
Okay.
Actually, I don't have many slides about this, and we're doing a lot of this is part of a larger research work.
Okay.
You can find more information about this. Maybe we can give you some references about how the things really work. Unfortunately, also Michele, who's the guy who's working on this algorithm, is not here. He's the main, I'd say, research head of Banksealer. He's a good person for asking questions, so if you would like to send emails to him, he would reply. So this is used for new users. When we have a new user, we don't know how to build the local profile. We use this. Any other question about this? Okay. So the last algorithm I'm going to talk about is the temporal profile. This is what I mentioned earlier. This is used to identify frauds transaction that looks good specifically, but if you analyze the user through a time of window, it looks stranger. It looks strange because for instance, the user performed too many transactions in a very small window, or the amount of the transaction was strange. Summing the amounts of the transaction, the result is strange. So how it works? It works similar to the local profile. What we have is different features. For instance, we have the amount of the transaction of the user, and we have the number of transactions of the user. And what we do is to compute an average for different time frames for a day, a week, and a month. And we store this model, we train this model, we store this information, we store this average and standard deviation. And then online, we try to apply this score considering how far from the mean and the standard deviation the actual behavior of the user was. This produced another score, and what happens is that those three models are merged together, and this is how we obtain a score that is the ranking measure we are using. Actually, this is it. As I was saying, there is some research paper about this, so if you want to have a look, you can find them here, or you just Google Banksealer, or we can send them to you. That's all. If you have any question.
I don't understand the relation of the two models that you presented. So the last one, do you use it with the first one?
Yeah, we use all the models together, and at the very end we merge the results. For instance, the way we merge the results is pretty different considering what we are doing. For instance, we use the temporal profile is pretty strange because it refers to a single user, not a transaction. I mean, if a user is performing too many transactions, this is an information that is related not to the specific transaction but to the user itself. So what we're doing is trying to weight differently as a user and increase his position if the user is behaving in a strange way. Something else we are doing is adding a label. So if the user is strange, so if he performed too many transactions, we're going to add a label on the interface so that the analyst sees what's going on. So there are different ways we are putting together those information. The basic behavior is just we sum them and we weigh different the different components.
And are you using any framework like Spark or Kafka Streams, just plain code?
No, plain code. We're actually using Kafka, but not any framework, no Spark, and not anything.
So all the statistics are computed on a relational database, if I understood well?
Partially, most of the work is done in memory in Scala, but we rely on a database, a relational database, for storing information.
And so Elasticsearch is only used for storing data to be used by the analyst.
Right. So we don't trust Elasticsearch being a good storage engine. It is not that way. So we're just using it for sending the transactions and for the analyst to analyze it, to adjust sort of.
Okay, thank you.
My question is, since you went for an approach where you try to go for an easy interpretability of the data by an operator, stuff like that, did you try to quantify the trade-offs of your approach? Meaning that maybe you are going for less false positives, then maybe you are losing something in terms of false negatives, or okay, you have features that are easy to see from an operator, but on the other hand, more complex features could give you better results. Did you try to quantify different approaches that go for more complexity and less interpretability?
Yeah, actually we try different approaches and different algorithms, and you have the results on the papers. Actually, since I'm not the scientific guy, I just have an half and half presentation, so I have half architectural and half scientific, and the scientific part is missing a lot of stuff. But we also tried a pure classification approach with neural networks, or I think it was like the random forest, but we didn't have very good performances. The main problem is what I mentioned earlier, so we have few fraudulent transactions, so it was pretty hard to have a balanced data set for running the algorithm.
The big problem is that there are all the limited number of researchers relying on real data in this context, because banks are not really happy to keep you and to let you work with their data. So and if I recall correctly, Banksealer is one of the only paper published with real world data. So the only work in terms of comparison was done by the Polytechnic Milan in the first instances of the research. And it would be like really good to have more scientific knowledge about this, but you have, again, you have to convince banks. Is the next NECST. So the PhD candidate was under Stefano Zanero, which is also one of the founder of Secure Network. And so it was kind of a mixed effort between the, I would say, security team and machine learning team. The other guy was Renato, I don't remember his last name, I'm sorry.
Okay, this is it. If you have another question, or we're good. Okay, so I think we're having some beer. Yeah. So I'm calling the guy. Thank you all.